Today's lesson is an overview of the periodic table. The modern periodic table is very recognizable by many people, but the original periodic table is shown here that was created by Dmitry Mendeleev. He was a Russian scientist or a Russian chemist at the end of the 1800s who had done a lot of research and work on the elements that were currently known, which, as you can see in the image, were not a lot of them. And he looked at their properties, he looked at their atomic masses, and he tried to organize these elements into some sort of pattern. So what Mendeleev did was he arranged the elements according to their atomic masses. And if you look at this version of his periodic table initially, you see that they do increase by atomic mass. He left blanks here because he knew that there were elements yet to be discovered that fit in terms of the atomic masses, but he also lined up these elements in terms of their chemical properties. So he recognized that there was a trend going across and down the periodic table. But again, there were many holes just because he didn't have all of the elements at his disposal at the time. I want you to look at your current periodic table, the modern one that we look at now. And I want you to take a look at the elements and tell me find three pairs of elements that are out of order according to their atomic masses. So you're going to notice that most of the elements increase in atomic mass. And I want you to find me three pairs, so two elements side by side, where the atomic mass is out of order. How is our current modern periodic table arranged? Well, our current table follows something called a periodic law. And this states that when the elements are arranged in order of atomic number, not atomic mass like Mendeleev had suggested, there is then a periodic repetition of their physical and chemical properties. And today, the periodic table is arranged according to atomic number, partly because at the time of Mendeleev's discoveries, the proton had not yet been discovered. And once the proton was discovered inside of the nucleus, they realized that there was a definite trend that every element had different numbers of protons. Most of the atomic masses also increase as you move along the periodic table, but as you just carried out a little activity, you realize there are some exceptions to that. So let's go over this version of the periodic table and talk about how it is organized. When we look at the periodic table, it's a strange shape, partly because of the way there's properties involved in the way that the chemicals are arranged or the elements are arranged. Partly because right here, we actually take out a set of elements from the main periodic table. Otherwise, it would stretch it out. It would be too long horizontally. But as we look at the periodic table, we notice that there are symbols. And every element has a symbol that is 1 to 2 letters. Some of them have 3 if they are an element that has just been discovered, but it doesn't have an actual name at the moment. But most of these element symbols correspond to the name of the element. There are some exceptions to this because when the elements were discovered, their Latin name was used. So I think of sodium, for example. Okay, so for sodium, sodium's Latin name is natrium, and that is why it is given the symbol Na. We no longer call it natrium. We call it sodium. We've given it an English name. The other thing you should notice is that the table is arranged in rows and columns. So the rows that go across are called periods. This is why it's called a periodic table. And one thing you should know about the periods as you move across, there are 7 of them, as you see right here. And those periodic rows correspond to the energy levels that each of those elements have surrounding the nucleus. So if you were to draw a Bohr-Rutherford diagram for lithium, for example, you would fill in electrons until you filled up 2 energy levels. Maybe not filled up, but placed electrons into 2 energy levels. If you came down to period 6 and you drew the Bohr-Rutherford diagram for radon, let's say, then you know based on the period number, it should have 6 energy levels. So that is a trend that we assume you know. Going down the periodic table in the columns, we call these columns that go down groups, or sometimes we also call them families. And the family is usually referred to more common groups of elements that we use. We're going to talk about 4 of them a little bit later. The groups go up and down. There's 18 of them, and we know that there's a little trend between groups and valence electrons. We've talked about this already. We skip over the transition metals in the center of the periodic table, and we know that groups 1, 2, 13 to 18 all follow this trend of the number corresponds to the number of valence electrons. And of course, groups 13 to 18, we lose the number 1. One other thing about groups is that the elements are arranged according to similar chemical properties. Okay, so everybody in group 1, okay, except for hydrogen, but sometimes hydrogen, they have similar chemical properties. And that is mostly true across the periodic table. The one set of elements that don't tend to follow this are these elements in the middle. These are called transition metals. And those transition metals tend to not follow the trends of the rest of the elements in the periodic table. One thing you should also be aware of is that elements are split on the periodic table according to metals and nonmetals and metalloids. So there is a staircase line that I am drawing in right here for you. And you should draw this in on yours as well. And that staircase line splits up our elements and categorizes them so that we have metals on the one side and we have nonmetals on the other side of that staircase line. Along the staircase line itself, those elements correspond to what we call metalloids, with one exception. Okay, aluminum is a metal. Okay, and that is very important that you know that aluminum is not a metalloid. Aluminum is a metal. As we mentioned down here, these 2 groups are called the lanthanides and the actinides, and they're given those terms because those are the names of the 2 elements that start off that those groups of elements. But basically, this is how essentially the periodic table is arranged. I want you to stop the video right now, and I want you to review what are properties of metals, nonmetals, and metalloids based on these elements of the periodic table. Now that you've jotted down some properties of our elements and our metals and nonmetals and metalloids, we're going to just comment on a couple other things before moving along. Notice on this particular periodic table, some of the elements are colored in or shaded in with colors. There are 2 liquids on the periodic table, and those are mercury and bromine. There are several gases on the periodic table, and the gases are mostly our nonmetals. So we'll see nonmetals over here, and of course we see hydrogen. Hydrogen is an exception. He is placed on the metal side of the periodic table, but he is not a metal. He is a nonmetal, but has properties of group 1 elements and valence electrons of group 1 elements. That is why he is placed over there. One thing that we want to comment on are the 4 main groups of families, and we're going to go over that together right now. So we have group 1 right here is called the alkali, pardon my bad drawing, alkali metals. And you've heard this term before. Alkali metals are very, very reactive metals. And hydrogen would not be part of this, just lithium down to francium. They are the most reactive metals that exist on the periodic table, and they all contain one valence electron. Group 2 metals right here are called the alkaline earth metals. And alkaline earth metals contain 2 valence electrons and are the second most reactive elements that exist on the periodic table. So you see some familiar ones there: magnesium, calcium. Those are important vitamins that we need for our bodies. If we skip over to group 17 and group 18 down here, we will take a look at each of those. Group 17 elements are called the halogens. And the halogens have 7 valence electrons. They are very reactive non-metals, and they're very common. So those, the fluorine, chlorine, bromine, iodine, they're very common ions that are bonded to many of our compounds that we use. And then our last group right here are called the noble gases. And noble gases have 8 valence electrons, except for helium. Helium only has 2, and they are inert. And inert is a special term you should know. It means that they are not reactive. They have full energy levels. They have no desire to react with anything. Some other aspects of the periodic table that you must know from your previous years are the relationship between valence electrons and ionic charges. So if we take a look at a halogen, let's say, so let's look at group 17 right here, and we pick any halogen. I'll pick fluorine because he's the first one. We know that the valence electrons, or the Lewis structure for fluorine, is drawn as such. Okay, we take 7 valence electrons and we move around the symbol and we place those electrons accordingly. What happens here is we know that elements want to have a stable outer energy level, and fluorine is so close. He just needs 1 more electron in order to pair up with that single and become stable. So because fluorine will gain 1 electron, fluorine ends up with an ionic charge of 1 negative. Okay, or sometimes we write it as -1. It's not particular to me which way you write it. We tend to write it this way. It's up to you what you want to do. If we look at an element from group 1, so for example, if we looked at potassium, who had 1 valence electron and wants a stable outer energy level, it doesn't make sense for potassium to gain 7 electrons to become stable. It makes sense for him to lose 1 electron and become stable by going down to the previous energy level. So what happens here is if potassium has lost an electron, he ends up with a +1 charge. If elements gain an electron, so the nonmetals, they end up with a -1 charge. So you need to know that relationship between valence electrons and ionic charges, whether those valence electrons are either lost or if they gain more to fill up the outer energy level, what are those corresponding charges?